When we talk about wave mechanics a lot, one of the things that we always want to try and establish is the difference between the movement of energy or the wave pulse versus the actual medium itself. And that's kind of highlighted in this diagram here. So you will see this series of graphs of amplitude as a function of position of the wave. So what it's doing is it's kind of tracking this wave over a period of 3 milliseconds. It's taking a snapshot at every half a millisecond. So to show you the idea of what a wave pulse is, or the traveling, or like kind of the speed of the wave, we're kind of fixing our attention on a crest, or at a point on a crest or a point on the wave. And what we're doing is we're following that as a function of time. So you see, as we follow that crest as a function of time, you can clearly see that that crest is moving. That is meant to show us that the energy in the wave itself, or that transfer of energy, or that wave pulse moving through this medium. So when we're trying to find the actual speed of the wave, in this case here, we see that this wave has moved a slight distance here, like probably this crest probably from here to here in a time of 0.5 milliseconds. We could use that to determine the speed of the wave. So that's meant to show kind of the speed of the wave or the pulse. But for an actual constituent particle in the medium, we always said that we want to just kind of say, especially if it was a transverse wave, all this particle can do is go up and down. So you'll see this particle here, and this actually works for a longitudinal wave as well, but you'll see this particle, as the wave passes through, you will see it kind of moving along with the wave, and then it's kind of doing its thing. So based on this wave here, if we call positive right and we call negative left, this particle is moving to the right, and now that it's below this axis, it's moving to the left, it's moving to the left, moving right, and so on and so forth. But that is the main thing. The medium kind of moves in response to the wave, executing simple harmonic motion. So this point in the medium is just going to oscillate about an equilibrium, whereas we can see that the wave pulse is actually traveling. And then, of course, when we talk about the speed of the wave, what we're really looking at is the speed of the pulse. So with that said, what we can do is we can kind of look at one more example. And this is an example from an old IB exam. And this is from May 2016. So it's a little bit of a challenging question. It gets a lot of people because wave theory and wave mechanics, to be honest, it's not a particularly easy thing to do. It's quite tricky. So we have a longitudinal wave. It's traveling in a medium from left to right. The graph shows the variation with distance of the displacement y of the particles in the medium. So we have displacement on this y-axis, and we have kind of the position of the graph, the position of the wave on the x-axis. So the solid line shows the displacement at t equals 0, and the dashed line shows that t equals 0.882 milliseconds. So we're told that the period of the wave, it happens to be greater than 0.882 milliseconds, and a displacement to the right of the equilibrium position is positive. All right, let's kind of dissect that last sentence. So a displacement to the right of equilibrium is positive. What that means on our graph here, anything above the equilibrium axis, this is what we're going to treat as going right. Anything below, we're going to treat that as going to the left. We're going to need that information later. So the first question on this exam is state what is meant by a longitudinal traveling wave. They just want you to show, do you know what a longitudinal wave is versus a transverse wave? So in a longitudinal wave, there's different ways to phrase it. Like, you don't have to phrase it exactly as it's written here, as long as you get the main idea. But, we could say something along the lines of the displacement of the particles, or you could say displacement of the mediums, or the medium, whatever you want. It's parallel, and parallel is kind of the key word. It's parallel to the direction of energy transfer. Now, if you want to say it's displacement of particles parallel to the motion of the wave or something to that effect, that's fine too. This is what I've written down. As long as what you say is close to this, or it kind of says the same thing, you're good to go. But that main word they'd be looking in here is parallel, whereas for a transverse wave, that displacement of particles is perpendicular to the direction of the energy transfer. So we'd like to calculate the speed of this wave. Now, we've used v equals f lambda to deal with waves. The problem is we don't know anything about frequency. We could certainly determine the wavelength, but we have to find another way to deal with this. Well, we know that v is equal to d over t. We know that for waves we can use uniform motion, but we need to find a d and a t. What we've been given in the question, the information we've been told that this solid line represents t equals 0, and then this dashed line represents the wave at a time of 0.882 milliseconds later. What we can do is we can find that distance the wave has traveled in 0.882 milliseconds. So looking kind of here at the starting point, I noticed that based on this starting point here and here, this is going to show us the distance the wave has traveled. Based on what I have here, I have a distance of 0.3 meters, and that distance has been traveled in 0.882 milliseconds. So I could say that the distance is 0.3 meters, and then we're dividing that by 0.882 milliseconds. So we've got to make sure that that ends up in seconds. We're going to multiply it by 10 to the minus 3. So if we do that, this is going to give us the speed of the wave. So we're going to get about 340 meters per second. So we can say that v roughly 340. So for this, based on it being a longitudinal wave and the fact it's traveling 340 meters per second, you wouldn't need to know this particularly for the exam, but this is most likely a sound wave. Sound wave is kind of our classic longitudinal wave. So that's the first part. What's the next piece that they're asking us to deal with? Well, they'd like us to now calculate the frequency. Well, we know that v is equal to f lambda. We just found the speed of the wave. We can get the wavelength from our diagram. So we know that the frequency is v over lambda. Now, if I look at the diagram, what I'm looking for a wavelength is I'm looking for a complete cycle. So I see here this wave, it'll perform a complete cycle here, and that represents this distance of the complete cycle. So I have this whole distance here. That's what I can call my wavelength. Based on this graph here, this wavelength is about 1.6 meters. So that's what I'm going to use in my calculation. So we have the speed that we just calculated from the previous question. So unrounded, I got about 340.14 meters per second. And then I'm going to divide that by the wavelength that we got directly from the graph. So if I do that, I'm going to get about 213 hertz. So I could say the frequency of this wave is about 213 hertz. Up to this point, the question has been pretty straightforward. There hasn't been really any IB content yet. Longitudinal wave is part of the Physics 20 program, finding the speed and frequency, also part of the Physics 20 program. C is where students would really get nailed, just because you have to kind of take what's on the graph and transcribe it into words, and you have to understand what the graph is saying. That's the tough part. So what are we being told for part C? We're told that the equilibrium position of a particle in this medium is at x equals 0.80 meters. So for the particle at t equals 0, we want to explain the direction of motion, and we want to state whether the particle is at the center of a compression or a rarefaction. So compression is kind of when the medium's tightening up, rarefaction is when kind of the medium's spreading out. So we want to state center of compression or rarefaction. So to look at the direction of motion, we need to go back to our graph. So for the graph, we're told that we're looking at the position of x equals 0.80 meters, and we're doing that for t equals 0. So we're looking on the solid curve. So here is our position of equilibrium. It's at y equals 0. That's great. We want to see what is happening to this particle after some time. Well, notice that a little bit of time later, at t equals 0.882 milliseconds later, you'll notice that this particle in this medium, at this position, well, it's now made its way down here on the graph. So 0.882 milliseconds later, this particle has shifted down on this graph. This is where it's now located. If it's going down on the graph, we were told that right represents positive. What that's telling us is that this particle has displaced to the left. So there's kind of two key points they'd be looking for on the exam. So first of all, we could say from the graph, particle moves down after 0.882 milliseconds. And it's important that you want to reference that you've gotten this from the graph. Like, you don't want to just say, yeah, it moves down. Like, where did you get that? We got this from the graph. And then we know that from this information, the particle has to be moving left. And this is based on the information stated in the context of the question. So on an IB exam, this question's worth 2 marks. You get 1 mark to kind of say, okay, well, how did you determine where this particle's going? So we could say from the graph, and then actually getting the direction right, so to the left. And, you know, most people could probably get that part, not an issue. It's the second part that gets people, and this is a very hard question. This is aimed at like the top end of students. So we want to state whether the particle is at the center of a compression or a rarefaction. So once again, what we'd like to do is we'd like to go back to our lovely graph. So here is the point in question. We're at x equals 0.8 meters. What we'd like to do is we'd like to look at what is happening to the particles around that point. So if I kind of go to the left here of this particle, well, we notice that our graph showing our amplitude, it's down in the negative regions. What that's telling us is that to the left of this equilibrium position, the particles are moving to the left. So I'm just going to draw some arrows showing that the particles over here are moving to the left. Now, if I go to the right of this equilibrium position, we're going to see that particles to the right of this equilibrium position, they are on the positive axis. So what we can see is that these particles are moving to the right. What you're going to notice is that on either side of this particle, what is happening is that, on either side of this particle at equilibrium, the particles surrounding it are moving away from this particle, so they're spreading out. What that's telling us is that this point here is at the center of a rarefaction. So we want to kind of write that out. So again, from the graph, particles to the left and right of equilibrium are moving away from the point at x equals 0.80 meters. So therefore, what we can say is that this is a rarefaction, or this is a center of rarefaction. So x equals 0.80 meters is the center of a rarefaction. And then we should just check on our diagram. If we have a rarefaction, the next equilibrium point should be a compression, then after that should be a rarefaction. So we're not asked to look at this, but let's just make sure that this does make sense. So if I go back to my diagram here, my next equilibrium position is going to be at this x equals 1.6. So just to the left of it, again, we have the particles, they are moving to the right here because it's in the positive axis. And then down below here, we have particles moving to the left, just because we're below this axis now. So you'll see that on either side of this equilibrium position, the particles are moving towards that equilibrium. They're kind of converging on this point. So this here would be a center of compression, which would make sense because we always want to have rarefaction, compression, rarefaction, compression. So this is an example of a really hard wave problem. If you get these, there's nothing about waves that the IB can throw at you to get you off your game.